Welcome back. I'm Steve Brunton, and today I'm really excited to tell you about the LASSO algorithm, which is a really powerful method from statistics for variable selection and for getting interpretable regression models that don't overfit to your data. Okay, so LASSO stands for Least Absolute Shrinkage and Selection Operator. This was introduced in 1996 by Robert Tibshirani, who is now a professor at Stanford. And this is one of the kind of early papers in the resurgence of sparsity in statistics, robust, interpretable statistics. Okay, so I'm going to walk you through the LASSO, what it is, how you can use it. This is really important. So if you're building models, let's say for physical sciences or for the field of health metrics or for making political or governmental decisions, you want those models to be interpretable. You don't want them to be overly complex, and you want them to have as few descriptive factors as possible, and that's exactly what the LASSO allows you to do. Okay, so I'm going to walk you through this. As with many other things in data science, it eventually boils down to a math problem like AX equals to B. So we have seen before that our regression problems often can be written as some matrix system of equations, A times X equals B, where we have measurements of this vector B. We know what this matrix A is, and we're trying to solve for some unknown X vector. And that's what our regression problem would be. Okay, so we're trying to find X that satisfies this equation. And in many cases, this matrix system of equations will not have exactly the same number of equations as unknown variables in X. So I might have more equations than unknown, which I've drawn here, this kind of tall, skinny A matrix. This is an overdetermined system, which means in general, you're not expecting to find a single unique X vector. There might not exist an X vector that exactly satisfies all of these equations because there's more equations than unknowns. So you don't expect X to satisfy all of these equations exactly. So we're looking for an X that approximately satisfies most of these equations. That's the problem you see a lot in statistics, where maybe I have, millions of observations and I'm trying to describe them with a few hundred explanatory factors. That's what we're going to think about. You could also have this in an underdetermined case where you have less measurements than you have unknowns, in which case, again, there might be infinitely many X's to choose from. Okay, so a lot of these regression problems boil down to how do you choose X so that it is kind of physically relevant and meaningful and interpretable for the problem at hand. So what I'm going to talk about today, I'm going to use this example of some kind of a health outcome. So let's say I have measurements for a lot of people, maybe tens of thousands or hundreds of thousands of people. This B vector could be, for example, the probability of developing heart disease or probability of developing heart disease in 5 years, maybe the probability of getting a certain type of cancer. Okay, so this would be some health outcome that you really care about that matters a lot. And the columns of A would be these kind of descriptive features that you measure for all of these individual people that you're collecting this data. So maybe you measure their age, their weight, their height, their blood pressure, heart rate, sex, how much calcium in their blood. So you do a full blood panel. You ask them a questionnaire, how much, do you smoke? If so, how much do you smoke? All kinds of things. And some of these are going to absolutely be relevant for the health outcome of, developing heart disease. Others might be less relevant. Maybe you ask them, what's your political affiliation? Or, do you have a dog or a cat? Things that, maybe that's information you do collect, but you don't think it actually matters for this health outcome. Okay, and so this is a big matrix regression problem. So we talked about this in chapter 1 of our book, Data-Driven Science and Engineering, on the singular value decomposition and the principal components. You can use that for these regression problems. And today we're going to talk about more sophisticated ways of handling this problem. Okay, so The basic idea here is that you're trying to do some kind of a regression to solve for x that satisfies this equation ax equals b. So you have a loss function, L, which we're going to say is ax minus b. How good does Rx actually fit the data? That will be encapsulated by this loss function. And by far the easiest, most straightforward thing to do is to use a least squares loss function. That's what people usually do. That's what you would do kind of just the simplest thing you would do is compute this least squares solution. And in general, you would write the optimization problem. So again, all of these regressions are optimization problems. You would write that optimization problem as argmin with respect to x of this loss function. So you're trying to find the x value that minimizes this loss function, and that's the x that you're going to use. That's what this argmin means, is that you're going to find the argument x that minimizes this loss function. Okay, and so the least squares problem, you solve that argmin with this loss function, just the standard least squares error loss function. But what you find is that when you use this least squares loss function in this kind of a regression problem, what you're going to find is that this x vector over here is going to be completely dense. You're not going to get any zero values. This least squares regression is going to tell you that all of your factors are important and all of them have non-zero entries in x. X is not going to be sparse at all. Okay, but we know, first off, that a lot of these factors probably don't correlate to health outcomes that matter. Maybe if I have a dog or a cat, or my political preference shouldn't really strongly correlate to my health outcomes. Then what you don't really want this x vector to be dense. What you want is for it to be sparse and have as many zero entries as possible. It's also really hard to interpret this model that you get from least squares, because this is saying that all of those factors are important. And maybe I have hundreds or even thousands of factors, columns of A that I'm measuring from. I don't necessarily want all of those factors present in my model. Okay, so there are things you can do to modify this regression to give it better properties and to make it more kind of physical and more interpretable and just kind of in general better. Okay, so the first thing I'm going to tell you about, this is probably one of the oldest besides least squares, is the ridge regression, also known as Tikhonov regularization. And this has been developed in the 40s to the 70s, so pretty old. And the idea here is that for many of these regression problems, even if it's underdetermined and the columns of A are not don't span all of Rn, where n is how many measurements I have, I might still have some of these columns being very parallel or kind of nearly linearly dependent. So for example, you might assume that, blood pressure and weight and smoking and heart rate, those might be pretty closely related. So patients that have high blood pressure and high, sodium in their blood might also have other columns that are correlated with that. I don't know. I'm not a doctor. I'm not a health expert. I'm making up an example. But you might have this A matrix, you might have the columns of this A matrix be almost linearly dependent for your data. And that would make this a very ill-conditioned regression problem. This regression problem would be very ill-conditioned because taking the pseudo-inverse of this A matrix is kind of worse and worse as the columns of A become more and more parallel or more and more linearly dependent on one another. And so what you find if you just do standard least squares on an ill-conditioned matrix like that A matrix, and you have maybe a little bit of noise in B, what you're going to do is amplify that noise, and your X vector that tells you how important these factors are is going to have really, really big positive and negative values, essentially trying to just kind of cancel each other out to fit the noise in B. So that's a well-known problem in inverse problems and in ill-conditioned regression in general that Tikhonov worked on for decades. And him and others introduced this regularization factor. This is called a regularization factor, this plus alpha x2 norm. And what that does is it says your new loss function, you're trying to minimize the error of the fit. You always want to minimize the error of the fit, but you're also going to penalize if x has too large of a variance or a deviation. Okay, so what that does is that it takes these kind of big entries, these big canceling out each other entries in X, and it tries to bring that variance down. And that has a nice regularizing effect for ill-posed problems. I mean, there's textbooks written on this. This is used everywhere. This is used in partial differential equations and statistics all across applied math and science. People use Tikhonov regularization, so it's a big deal, okay? But you still get a model that is essentially dense. All of the entries of X are non-zero, and so your model is still very complicated in terms of, it needs all of the explanatory factors to describe the outcome. And that's where the LASSO comes in. So this 1996 algorithm by Tibshirani, this LASSO algorithm, is very similar to ridge regression in spirit. It's similar to this Tikhonov regularization, but instead of a 2 norm on your vector X, it adds a 1 norm on your vector X as a penalty. And so as we've seen many, many times before in this lecture series, the 1 norm promotes sparsity. So if you force a vector to have a small 1 norm, generally what that does is that it tries to make as many entries of that vector 0 as possible, that it can make 0. And so this LASSO regression has, again, it still has this error term that we're trying to minimize the error of the fit. We still want a good model fit, AX equals B, but we want X to be as sparse as possible and have as many 0 entries as possible. And this does a pretty amazing thing. So now if you look at the model you get when you run this LASSO regression, and again, this is just a cartoon, this is not real data, this is not a real example, but in this cartoon example, when you run this LASSO regression with this L1 penalty, what you find now is that your X vector is very sparse, and it highlights only a few columns of this A matrix that are most correlated with your desired health outcome, with, in this case, whether or not you're likely to develop heart disease, okay? And it might pull out factors such as, blood pressure, heart rate, if you're a smoker. I don't know why I had this column here for sex. I just picked kind of these columns a little bit at random. But the basic idea is that this LASSO regression will highlight a few columns of the A matrix, and this has a really, really big impact in your resulting model. So for example, doctors and politicians are groups of people who notoriously trust their gut when they're making decisions. Okay, so they of course pay attention to data and read, the leading journals and listen to other experts, but they also have kind of a gut feeling. They want to be able to explain why they're taking the actions they're taking. And so if you have 2 models, one of which has 100 factors that matter, and another model that only has 4 factors that matter, the 4-factor model, if it's almost as good at minimizing the error, that's a better model because it's easier to interpret, it's easier to communicate, and it's easier to make decisions based on that model because it's just simpler, okay? And again, that goes back to our principle of parsimony that we've been talking about, that somehow sparsity can be a good thing because it is the simplest model that describes your data. Okay, so that's what this LASSO allows you to do. And it can also help prevent overfitting. So if I have all of these columns of A and I get to fiddle with all of their coefficients, like in this least squares, I might overfit to my data in B. The LASSO is a little bit more robust. It can help you prevent overfitting because it's only selecting the variables that are most important to that desired outcome. Okay, and so kind of least squares has been around, for a really long time. I don't want to say that they were, writing this on cave walls, but this is an old algorithm. Tikhonov regularization is from kind of the 40s to the 70s. Okay, so this is also, by modern standards, somewhat old. LASSO was developed in 1996 and has taken off since then. So this is used a lot since it was introduced. You also have this elastic net algorithm. This is a really cool algorithm where essentially it has the same LASSO penalty, but it adds back in the ridge penalty. So it kind of balances the LASSO and the ridge penalties and has better properties. So a lot of times you really want to use this elastic net. It kind of gets the best of both worlds. And just kind of an interesting fact for those of you who are into machine learning, in 2014, there was a cool result that connected elastic net to support vector machines. Basically said that they're closely related algorithms. So I thought that was kind of neat. Okay, good. And so we've seen this picture before about how the L1 norm, because it's kind of a pointy, the level sets of the L1 norm are pointy, it promotes sparse solutions. So if this blue line is the line of all possible solutions, it's going to intersect my L1 norm minimum solution at a sparse solution, whereas the standard least squares 2 norm is kind of round and is going to intersect at a non-sparse solution. This picture was actually in that original 1996 paper by Tibshirani. So he was already showing us kind of graphically why the L1 norm has this really, really nice sparsifying property. And I think this is actually one of the reasons that paper was so successful, is because it gave a very clear kind of pictorial explanation of why and how this algorithm works. So that's really neat. Okay, good. So we have this basic lasso regression problem. We're trying to minimize the error of our fit, and we're trying to promote sparsity with this lambda 1 norm of x. In MATLAB, there's a built-in MATLAB command LASSO, so you can play around with LASSO. In Python, you can use sklearn. In the linear model, there's a LASSO command. And again, all of this material is in chapter 3 of our new book, Data-Driven Science and Engineering by Nathan Kutz and myself. And we have all of this code for all of these examples on our website, databookuw.com. I'll put a link in the comments. Okay. And so when you run this LASSO algorithm on a problem, this is actually from the original 1996 LASSO paper, what we're going to see is kind of this is the magnitude of the coefficients of that vector x as you sweep through different lambda values. So this lambda knob here essentially allows you to tune how sparse you want your solution to be. So if I have a really, really, really big lambda value, I'm going to get an ultra sparse model because I'm penalizing terms in x so much. So this is in 1 over lambda here. So if lambda is really, really big, then 1 over lambda is almost 0, and I get, either 1 term or eventually no terms. And as I relax that lambda, as I make lambda smaller so that I'm kind of balancing these two error and sparsity terms a little bit more, you'll see these terms kind of pop up. Now I have a second term describing my data. Now I have a third term and a fourth and a fifth, sixth, seventh, eighth. And eventually, in the limit where lambda is 0, you recover the least square solution. So that's a really nice property of the lasso, is that if you just have lambda 0, you recover your standard least square solution where all of the terms are important. Okay, and so that's pretty cool. You can actually kind of tune how sparse you want your model, and you can watch, this is called I call this the lasso path. You can see kind of as you sweep through lambda, what terms turn on or turn off at different times. So this is super useful to see kind of what model you want to use. Okay, really interesting paper I think everyone should check out. Basically, false discoveries occur early in the lasso path. That means as you're sweeping out this lasso path, and often we sweep from left to right. I'm sorry, I said that exactly wrong. From right to left. Often we sweep from small lambda up to big lambda, from small lambda to big lambda. And essentially what happens is once a term dies, it can never come back in this iterative procedure. And so once this term is dead, it's never coming back. And if it accidentally kills an important term too early, for whatever reason, it's never coming back. And essentially what this paper is showing is that that often happens, and it often happens very early in this lasso path. So there are some algorithms that kind of fix this that I might talk about later, but it's actually a pretty recent result, and it's really important if you use lasso, okay? The other thing I want to show, and this is actually a figure from our book, this is from chapter 3 of the book, and again, this is as you can see the x-axis, we're actually decreasing lambda from left to right again. You can see that if you look at the mean squared error, as you, essentially you can picture this as you go from left to right, you are adding more and more terms in your model. So your model is getting more and more complex as you make lambda smaller and smaller. And as you make your model more and more complex, as you add more and more terms, you see that your error actually does drop down. But this is cross-validated error. This is on a holdout data set that I didn't use to train. And so at some point, when my model becomes more complex, at some level of complexity here, kind of in this left plot, at some level of complexity, I actually start to increase my cross-validated error because I'm adding in terms that are not actually correlated with my outcome. So this is really, really nice. What this shows is that LASSO is also really good for preventing overfitting. Okay, so this is showing that as you add more and more terms, your error decreases, and then eventually starts to increase when you have the right lambda value. So this allows you to choose the correct lambda value, and the correct number of terms in your model is through cross-validation. So that's really nice. You see that some level, some sweet spot of sparsity gives you models that are the most accurate without overfitting. Okay, so that's really cool. And I showed you this kind of picture from the original Tibshirani paper. This is a slightly, cooler 3D version that we made for this recent paper in IEEE Axis. And there's this algorithm that was introduced by myself and colleagues, and you should read about this. This is a really cool algorithm called Sparse Relaxed Regularized Regression, SR3. This is by Peng Zhang and Sasha Aravkin, kind of on the end caps. And the idea is when you're solving these kind of sparse optimization problems, when you want a solution that simultaneously has low error and good sparsity properties, this is the classical picture that you see from kind of the LASSO perspective. But it's possible to relax your regularization problem and write it in a slightly different form so that you get better numerical properties. Basically, this oval and this diamond become a little bit more normalized in these relaxed coordinates, and it's much faster to converge down. I don't know if you can see this blue path here is kind of how long this iteration takes to converge to the sparse solution. And with SR3, it converges more rapidly and more robustly. So this actually solves that problem that was brought up in that Candes paper about basically the LASSO path breaking down early. Okay, so I highly encourage you to check out this SR3 paper. It's pretty cool. And it can actually be used to improve many of the sparse optimization problems we've talked about, from sparse regression like LASSO, matrix completion like robust principal components analysis, compressed sensing, and total variation problems. Okay, so I've definitely talked about at least 3 of these in this lecture series. But you can use this SR3 framework in all of these. And the code is open source, so you can download it and get going on your research problem. Okay, so before I conclude, I just want to talk a little bit about how we use this in model discovery. We do a lot of dynamical systems discovery, modeling complex systems that evolve in time. So this is different than what the statisticians would do, where you have some kind of static health outcome as some function of all of these measurements that you take right now. What we want to do in the physical sciences and in engineering and control systems is we want to model dynamical systems like rockets, being launched to the moon, and maybe your metabolism as it changes over time, things like that. Okay, and so we have this algorithm, the sparse identification of nonlinear dynamics, or the SINDI algorithm, that uses this kind of LASSO idea to discover nonlinear dynamical systems. So here, if you had data from a simulation, maybe you had the derivatives x dot, y dot, z dot, and you had measurements of the system state x, y, and z, you could build a library of candidate terms that would be in the right-hand side of the nonlinearity. You could build this library. And again, this starts to look like a sparse regression problem, like a LASSO problem. You want to find the fewest columns of this matrix that add up to equal x dot, y dot, and z dot. Okay, so you want a sparse Xi vector here, or Xi matrix, that multiplies this feature library to predict the derivatives. And once you identify this sparse pattern of terms, essentially what you get is the original dynamical systems in this case, and you can then run simulations on this model. So this allows you to actually discover purely from data, just from measurements of x, y, and z, and x dot, y dot, and z dot, you can discover the nonlinear dynamical system that generated that data. In this example, we know the answer, so we can compare against that as a benchmark. But since then, we've applied it to lots of systems where we don't know the answer. And again, this looks a lot like a sparse regression problem. We don't use LASSO per se. We use a sequentially thresholded least squares algorithm that's in this PNAS paper, but it's morally very similar to the LASSO problem. Okay, so again, you have this big regression problem. In this case, b, ax equal b. My b is my derivatives. A is this library theta of candidate terms in the right-hand side of my dynamical system, and C is my X vector. So kind of A, X equals B. And we're trying to find the sparsest C vector or X vector that describes those derivatives, that models the data. So this really is a dynamical systems model, just like those LASSO models. And it happens to have the same basic features. It's more interpretable. It generalizes better because it doesn't overfit and things like that. And so I remember I've been talking about parsimony and kind of just this principle of the simplest solution often being the best one. So I want to talk a little bit about that in the context of this dynamical systems modeling. So again, we have this lambda parameter, which is what allows us to control the sparsity. And so as I increase or decrease lambda, I'm going to get models that are more or less complex. Okay? And so what we're going to do is we're going to plot on this error versus complexity term the different models we could get. So if lambda was if lambda was infinity, if I made lambda really, really large so that I penalized sparsity so much, I will eventually get the trivial model x dot equals 0. It'll have no terms. And that's clearly underfit. It's very simple in terms of complexity, but it's got a huge amount of error. Okay? On the other extreme of the spectrum, if I have lambda equals 0, so I'm not penalizing sparsity at all, I get my least squares solution. I have very, very low error, but a tremendously complex model in terms of the number of terms. And what you hope is that there is a family of models between these two that kind of balances complexity and error. And even more, you hope that it looks like this. You hope that there's some sweet spot, some kind of elbow on this Pareto curve where you get a model that has really low error and really low complexity. This kind of sweet spot that balances accuracy and efficiency of your model. This is where your parsimonious kind of good models live. Okay? And it's important to note that if you actually cross-validate your models, your least squares solution doesn't have as low of an error as you maybe originally thought. When you cross-validate, you find that your least squares solution probably overfit because it had too many terms. Okay, so that's what you get up there. And again, these cross-validated parsimonious models like Cindy live in this sweet spot that balance complexity and cross-validated error. Okay, and so some references here. We're not the only ones that do parsimonious modeling. There's lots and lots of groups that do this. You can also use this SR3 optimization and model selection. So there's lots going on here that I'm not talking about. But I really just wanted to kind of point out in general that you can use the LASSO for all kinds of problems, both in classical statistics and statistical modeling to dynamical systems modeling. There are new optimization frameworks like this SR3 optimization that can do, in a lot of cases, really more efficient and more robust sparse regression. And so that's pretty cool. Again, if you're interested in this, please check out our new book, Data-Driven Science and Engineering. This is a Cambridge book. All of the code and video links are on databookuw.com, and you can download the PDF here. If you like this, if this is helpful, please like, please subscribe, write comments, tell me what more you want me to talk about. And there's going to be a lot more on sparsity and how to use these methods, so stay tuned for more. Thank you.